Hello and welcome to The Explainer. Today, we're jumping into two words we throw around all the time: temperature and heat. And they seem pretty straightforward, but the real difference between them, it's the key to understanding, well, pretty much how the entire physical world works. So, to get our brains warmed up, here's a little puzzle for you. Which do you think has more total heat energy? A single tiny lit match or an entire swimming pool on a summer day? Now think carefully, because the answer isn't as obvious as it looks. And stick with me, because by the end of this, you'll know exactly why. All right, to crack that puzzle, we first have to get our terms straight. It really all boils down to nailing the crucial difference between what we mean by temperature and what we mean by heat. Okay, let's break this down. On the one hand, you've got temperature. The key word here is average. Imagine all the tiny particles in an object are jiggling around. Temperature is just a measure of their average jiggle speed. A high average jiggle, that's a high temperature. But heat, on the other hand, isn't about the average. It's the total amount of energy that's actually moving from a warmer thing to a colder thing. It's pure energy in motion. So, if temperature is our measure of hotness, how do we actually, put a number on it? Well, for that, we need some reliable tools, and maybe even more importantly, we need some scales that we all agree on. And the tool for that job is, of course, the good old thermometer, or termómetro, as it's called in our source material. Its entire purpose is to give us a hard number for that degree of hotness, basically giving us a sneak peek at the average energy of all those jiggling particles. Now, this is where it gets really interesting. This table shows the two big scales in science. We all know Celsius, right? It's based on something we can all relate to: water. 0 is where it freezes, 100 is where it boils. But scientists often prefer the Kelvin scale. Why? Because it's an absolute scale. It doesn't start with water, it starts at the coldest possible point in the entire universe. And that coldest temperature has a name: absolute zero, or zero assoluto. At 0 Kelvin, that's minus 273.15 degrees Celsius, everything stops. All that particle jiggling we talked about just ceases. It's the lowest energy state possible. You literally cannot get any colder. It is a fundamental law of the universe. So, now we've got a good grip on temperature, let's switch gears and get back to its wilder cousin: heat. If temperature is like taking a snapshot, then heat is the action movie. It's the energy that actually makes things happen. Okay, this is a really important point. An object doesn't really contain heat. Heat is just the name we give to energia in transito, energy that is actively flowing from a warmer place to a cooler place. As soon as that energy gets where it's going, it becomes part of the object's internal energy. But the process, the transfer itself, that's what we call heat. So how do we count this flowing energy? Well, the standard scientific unit is the joule, but you'll definitely recognize the other one, the calorie. And yep, it's directly related to the food calories we see on nutrition labels. At the end of the day, it doesn't matter if you're heating water or fueling your body. It's all just a way of measuring energy. Now, here's a cool thing. Not everything reacts to heat in the same way. This is where a property called specific heat, or calore specifico, comes into play. You can basically think of it as a measure of how stubborn a substance is, how much energy you have to dump into it just to make its temperature go up. And this is the perfect example. Think about a day at the beach. The sun is beating down, hitting the sand and the water with the exact same amount of energy. But look at this chart. Water has this massive specific heat compared to sand. It takes almost 10 times more energy to raise the temperature of water. And that's exactly why the sand gets scorching hot while the ocean stays nice and cool. So that whole idea of pumping energy into something leads us right to our next point. Adding heat doesn't just make things feel hotter. It can physically change the very nature of matter itself. The first and most common effect of adding heat is something called thermal expansion, or dilatazione termica. It's the reason sidewalks have those little gaps in them and why huge bridges have special expansion joints built in. And how it works is actually pretty simple. When you add heat, those little particles we've been talking about, they don't just jiggle faster, they jiggle wider. They start taking up more space, bumping into their neighbors and pushing them away. When you get billions and billions of particles all doing that at once, the entire object actually gets bigger. It expands. But if you keep pumping in the heat, you get an even bigger effect than just simple expansion. You can actually force a passaggio di stato, a complete change of state, like turning a solid into a liquid. We see this journey every single day with water, right? You start with a solid, ice. You add some heat, it goes through fusion or melting and becomes a liquid. You keep adding heat, it undergoes vaporization or boiling and becomes a gas. Steam. And this brings us to our last and honestly most fascinating concept. It turns out there's a kind of secret, hidden energy that's at work whenever these changes of state are happening. Let this sink in for a second. You've got a pot of water on the stove. It hits 100 degrees Celsius and starts bubbling away. It's boiling. Now, what happens if you crank the heat up even higher? The water just boils more violently, right? But the thermometer, it stays locked in at 100 degrees. So where's all that extra energy going? And the answer is latent heat, or calore latente. The word latent literally means hidden. It's hidden energy. During a phase change, that extra energy you're adding isn't making the particles jiggle any faster. Instead, it's being used for the really hard work of literally breaking the bonds that hold the particles together as a liquid. There are two main types you'll run into: the latent heat of fusion, that's the energy you need to melt a solid, and the latent heat of vaporization, the energy you need to boil a liquid. This hidden energy is exactly why a burn from steam is so much worse than a burn from boiling water. That steam releases all that hidden vaporization energy the second it condenses on your skin. Which brings us all the way back to the beginning to finally solve our puzzle. Which has more heat energy? The swimming pool, absolutely. The match has a ridiculously high temperature, right? Its particles have a super high average energy. But the pool, despite its lower temperature, it has an unbelievable number of particles. And the total energy of all those gently moving water molecules is just astronomically bigger than the total energy in that one tiny hot match. So there you have it. Temperature is the average jiggle, heat is the total energy in transit. It's like the difference between one person running really fast and the total momentum of a massive, slow-moving crowd. Now that you know the rules, what are you going to see differently? From the chill of the ocean on a hot day to the steam rising from your coffee, it's all a little clearer now, right? Thanks for joining us on The Explainer.